Hi, this is Mrs. Doris. This is Tuesday, November 5th, and we have warm-up 2 as well as lesson 5-2 regarding direct variation. Pause your video at this time, and if you are doing this at home, you may not be able to do number 2, although it might be fun to do that with maybe one of your parents or a brother or sister and use their birth date as well as your birth date in order to find the slope. If you have any questions about this, you might refer to lesson 5-1, or please bring your questions to me before or after school. All right, beginning lesson 5-2 entitled Direct Variation, our objective today is that students will write and graph an equation of a direct variation. And our reason for studying linear functions in this chapter, of which direct variation is a linear function, these are very useful in solving real-world problems. We have some vocabulary today. First of all, direct variation is when the ratio of two variables is constant. Also, the relationship can be represented by a function in the form of y is equal to kx, where k is not equal to 0. So, an example of direct variation would be y equals 5x, or y equals 1/2 x. Notice that the k is always going to be a number, and your equation will have y equal to some number times x. Our next vocabulary term is constant of variation for a direct variation, and that's the coefficient of x, or the k, in the above formula, y equals kx. So in my previous two examples, y equals 5x, 5 is the constant of variation. All right? To determine whether an equation represents a direct variation, solve it for y. If you can write the equation in the form y equals kx, where k is not equal to 0, then it represents a direct variation. All right, so let's go to problem 1, and we're going to identify whether or not this expression represents a direct variation. All right, so we start out with 4x plus 5y equals 0. And we're going to go back. This was chapter 3, or 2 maybe, I believe, where we were solving for y. And if I circle my variable term, that shows me that I've got to get rid of the 4x. So I'm going to subtract the 4x in order to remove it from the left side of the equation and put it on the right side of the equation. All right, my 4x minus 4x is 0, so I have 5y is equal to negative 4x. In order to isolate the y and undo the multiplication of 5 times y, I'm going to divide by 5. 5y divided by 5 is 1y. And on the right side, I have negative 4x over 5, which can also be written as negative 4/5 times x. This is in the form of y equals kx, and our k is the negative 4/5. So the constant of variation, k, is negative 4/5. And that would be the answer to the above question. And is it direct variation? Yes, it is, because it is in the form y equals kx. Does 2x plus 3y equal 4 represent a direct variation? And if so, find the constant of variation. All right, well, we're going to follow the same procedure that we used before. I always suggest that you circle the y term, including its coefficient, as well as any operation that comes before it. Plus makes it easy, but if it's a minus, then that would have been a negative 3y. All right, so once again, the first thing that we have to do is to remove the 2x from the left-hand side. 2x minus 2x is 0, and 0 plus 3y would simply be 3y. On the other hand side, we have 4 minus 2x, which we cannot combine because they are not like terms. And I'm going to rewrite this so that my x term is first, my minus 2x, and because the 4 is positive, it will be plus 4. My last step is to separate the 3 from the y, and because it's multiplied together, we're going to divide by 3. And we have to divide the whole other side by 3 as well. 3y divided by 3 is 1y. And we're going to separate these now. I have negative 2x over 3 would be negative 2/3 x. And 4 over 3 would simply be 4 over 3. There's really no need to change that to a mixed number, but it would not be wrong to do so. So you could say plus 1 1/3. All right, now, is this in the form of y equals kx? Well, this first part of the equation is. However, we have this plus 4/3 added on, and because of that, our answer is no. This is not a direct variation, because it is not in the form of y equals kx. So our answer is no. And so we do not have a constant of variation. Problem 2, writing a direct variation equation. Suppose y varies directly with x, and y equals 10 when x equals negative 2. What direct variation equation relates x and y? All right, well, we have 2 steps to do this. Our first step is to find the constant of variation. So we're going to begin with our little formula, y equals kx, and we're going to use the information we know. We know that y is 10 when x is negative 2. So our first goal is to find the constant, k. All right, well, dividing both sides by negative 2, my negative 2's would cancel out, and k is going to be equal to 10 divided by negative 2, which is negative 5. All right, so we have accomplished step 1. Now we're ready to write the equation, substituting the constant for k. So, using our y equals kx, we go back to y equals, and because k is negative 5, we are going to put the negative 5 where the k is, and then multiply it by x. So this is my direct variation equation for this problem. What is the value of y when x is negative 15? That's simply a matter of substituting in our new formula, y equals negative 5x, the negative 15 for the x. And so negative 5 times negative 15 would be 75. Problem 3. Graphing a direct variation. Weight on the moon y varies directly with weight on Earth x. A person who weighs 100 pounds on Earth weighs 16 and 6/10 pounds on the moon. What is an equation that relates weight on Earth x and weight on the moon y? What is the graph of this equation? All right, uh, weight on Earth is x. So let's just label 100 pounds on Earth is our x. 16 and 6/10 pounds on the moon is our y, since moon is represented by the variable y. So let's first of all write our direct variation equation. Y equals kx. We're going to use our values 16 and 6/10 for the y and 100 pounds for weight on Earth in order to find our constant of variation k. Okay, dividing both sides by 100 so that we isolate the k. Our constant 16.6 divided by 100 moves the decimal point over a couple of places, so we have 0.166 for our constant. All right, going back now then to our original formula, y equals kx, we're going to substitute in 0.166 for our constant of variation. And so our equation is going to be y equals 0.166x. All right, to graph this equation, the best way to do it is to make a table. And you probably will want to grab a calculator. All right, a good value to start with for x is 0. 166 thousandths times 0 is simply 0. So on our graph, if this is our y-axis, which is our weight on the moon, and x is our weight on Earth, zero, zero is going to be right there. All right. All right, choosing some values that will help us graph this before we determine our scale. Weight on Earth, we might use 50 pounds. 100 pounds, we happen to know already is 16 and 6/10. Let's go ahead and do 150 and 200. All right, and this should give us enough points that we are able to graph. So, substituting 50 in for the x, we're going to take 0.166 times 50, and we get 8.3 pounds on the moon. Taking 1.66 times our 150 pounds, we get 24.9 pounds on the moon. And taking our 0.166 times 200 pounds on Earth, we get 33.2 pounds. All right, so let's determine a nice scale and graph this. I think I'm going to, on our weight on Earth, we'll make every other one 50 pounds. All right, so this would be 100 here, this would be 200 here. For our scale, For weight on the moon, let's go by, doesn't matter, let's go by tens. This would be 10, 20, 30. All right, so 50 pounds is 8.3, would be about right here. 100 pounds, 16, right above. 150 is 24.9, and 200 pounds is 33. All right, now, if I had these drawn, maybe there's a better scale to use, but it is a direct variation and it should be a straight line. All right, problem number 4, writing a direct variation from a table. For the data in the table, does y vary directly with x? If it does, write an equation for the direct variation. All right, for problem number 4, as we look at the data in the table, let's go back to our direct variation model, y equals kx. If I were to take this equation and divide both sides by x, my x's would cancel out on the right-hand side, leaving me with k. And on the left-hand side, I simply have y divided by x. So, as we look at a table, if we take each y and divide it by the x, and we keep getting the same constant, then we would have a direct variation. So, let's do that. We have 2.25 divided by negative 3. We have negative 75 hundredths divided by 1. That one's easy. That would simply be negative 75 hundredths. And negative 3 divided by 4, which if you express as a decimal, it would be negative 75 hundredths. Okay, so those two, let me go ahead and put my 0 here. All right, so the only one that we really need to check is 2 and 25 hundredths divided by negative 3. And once again, we get negative 75 hundredths. So because all of these are the same, we can say yes, y does vary directly with x, and our equation would be, going back to our model, y equals kx, all we do is substitute that constant, negative 75 hundredths, into the equation. And that would be our equation for the direct variation. Y equals negative 75 hundredths times x. All right, so to summarize our lesson today regarding graphs of direct variations, the graph of a direct variation equation y equals kx is a line with the following properties. Number 1, the line has to pass through 0, 0. In order to be a direct variation, it must go through 0, 0. And the slope of the line is k. When the constant k of variation is greater than 0, you see we have a line that is going upward from left to right. And of course, if k is greater than 0, the slope is positive. In the graph on the right, if k is less than 0, which means that the constant is a negative number, then we have a line that is going downward from left to right and has a negative slope. All right, your assignment today is on page 304 and 305. Please do 9 through 33 odds. And if you have any questions, please be sure to ask.